In the third lecture, we will see the intrinsic carrier concentration in semiconductor. The topics to be covered are the density of states function, intrinsic carrier concentration, law of mass action, Fermi energy level for intrinsic semiconductor, and the band model for silicon. We look at the energy band diagram of silicon. Assume that we have a silicon bar. This is x equal to 0. X equal to L. So we draw the energy band diagram with respect to the free space energy level. This is E0, the vacuum energy level. Below that we have the conduction band. The edge of the conduction band EC. The difference between these two levels, it is the electron affinity E psi, which is 4.05 electron volt for silicon. And we have the valence band. The conduction band and the valence band, they differ by a band gap Eg, which is equal to 1.1 electron volt for silicon at T equal to 300 Kelvin. So if you look at the silicon, the number of silicon atoms plus per centimeter cube, we got this answer as approximately 5 multiplied by 10 to the power of 22 atoms per centimeter cube for silicon. So if you look at the conduction band and the valence band, the conduction band contains foreign states, the valence band contains foreign states. So there are foreign states vacant in the valence band and foreign states filled in the there are foreign states vacant in the conduction band and foreign states filled in the valence band. So foreign corresponds to 20 multiplied by 10 to the power of 22 per centimeter cube. This many number of states are available. Look at the bond model of silicon. Bond model says that the silicon atoms normally forms covalent bond. Covalent bond, which is normally considered as the strongest bond, the strong bond. We know that what is the bond energy, that is equal to band gap energy. Bond energy is equal to the band gap energy, which is equal to Eg, which is 1.1 electron volt for silicon at T equal to 300 Kelvin. So we know that if the energy E is greater than Eg, what happens is bonds can break. The bonds can break. This will generate electron hole pairs. EHP is generated. Okay. So what is the effect of temperature? Assume that we have a free electron here. The free electron gains thermal energy. And collide with this silicon atom. What happens is this bond can break. So this covalent bond will break. When a covalent bond breaks, what happens is there is one free electron created. So there is a free electron available here. The free electron can rotate over a wide radius. So that free electron this is a free electron, and there is a vacancy existing here. Vacancy, or we call it as a hole, existing here. So what happens as the temperature increases, bonds will break. There is a breaking of bond, covalent bond, and due to the breaking of the covalent bonds, electron hole pairs are generated, EHPs are generated. So this we call it as thermal ionization. This process is called thermal ionization of silicon. So we want to look at the thermal energy. What is the energy of the electron? If we look at the free electron in silicon crystal, it is similar to a gas molecule in free space. Gas molecules in free space. The only difference is the electrons are moving in a silicon crystal, whereas in free space the permittivity is 1, relative permittivity is 1. So what is the kinetic energy of the gas molecule? The kinetic energy of a gas molecule, this is the average energy, that is equal to K T, that much joules. Where K is the Boltzmann's constant, which is 1.38 multiplied by 10 to the power of minus 23 joule per Kelvin. So by substituting this value at T equal to 300 Kelvin, so what is the kinetic energy of gas molecule? That is equal to 0.026 electron volt, will be equal to 26 milli electron volt. Hence we can say that this implies that the thermal energy of the electron is the kinetic energy of the gas molecule. And is equal to 0.026 electron volt. That is the energy of the electron at room temperature. So what is impact ionization of silicon? We have a silicon atom. This is a silicon atom. So we have a high energy electron, okay, is coming and hitting the silicon atom. It will break the bond. So it will generate a free electron as well as a vacancy, which is a hole. So this we call it as electron hole pair generation, EHP generation. So this process of generating electron and hole, we call it as a impact ionization. Impact ionization of silicon. And we know that to break the bond, what is the energy required? Must be greater than or equal to the band gap energy Eg. That is greater than or equal to 1.1 electron volt for silicon. But what is the kinetic energy of electron at T equal to 300 Kelvin? The kinetic energy is equal to K into T. That much electron volt, which is equal to 0.026 electron volt. Remember, 1 electron volt is 1.6 multiplied by 10 to the power of minus 19 joules. So you have answer in joules, convert into electron volt. So what is the carrier generation mechanism? An electron colliding with the silicon atom will generate the electron hole pair. But how many number of electrons are required to break the bond? The number of electrons required to break the bond that is equal to bond energy divided by the kinetic energy. The bond energy is Eg, kinetic energy is kT. So that is equal to 1.1 electron volt divided by 0.026 electron volt. That goes approximately 42. 42 electrons are required to break the bond. If assume that P is a probability that an electron will collide with silicon atom. If P is a probability that the electron will collide with silicon atom in a statistically independent process, in a statistically independent process, what is the probability that the probability that 42 electrons will converge at one silicon atom will be equal to P raised to 42. Remember, P raised to 42, this quantity that is negligibly small. negligibly small, because we know that the probability is bounded between 0 less than or equal to p less than or equal to 1. So since the p is always less than 1, the p raised to 42 will be very small value. So how many bonds will break? Negligible amount of bonds will break inside a silicon. So what are the total density of states in the conduction band and valence band? When you consider 1 cubic volume, so this is 1 centimeter, 1 centimeter, 1 centimeter. It is 1 centimeter cube volume. If you consider the number of silicon atoms, n silicon, we know that it is 5 multiplied by 10 to the power of 22 atoms per centimeter cube. Now in valence band and conduction band, we have foreign states. So valence band contains foreign states, conduction band contains foreign state. So the total density of states, so we can say that conduction band foreign empty and valence band foreign filled. This is the density of states in the valence band and conduction band. The density of states in valence band and conduction band. The density of states approximation denoted by G of E. So you can see that in valence band and conduction band, the distribution of states, distribution of energy states over the energy level levels are non-uniform. It is a non-uniform distribution of states. So the non-uniform distribution we can show like this. So this is E in electron volt. So this is the edge of the conduction band. This is the edge of the valence band, separated by a band gap Eg. So the distribution of states is non-uniform. Therefore, we can approximate the distribution by using a parabolic curve like this in the conduction band, and just by using a parabolic curve in the valence band. So this approximation, we say it is Gc of E, and this approximation we write Gv of E. The distribution of energy states over the energy level is non-uniform. So we approximate this by Gc of E and Gv of E. Okay. Normally the approximation we use parabolic density of states approximation. parabolic density of states. It is a better approximation because the distribution is not constant, the distribution is not linear. So the next possibility is a nonlinear distribution, and that nonlinear distribution we take it as parabolic distribution. So what is the expression for G of E? This is E in electron volt. So we have the conduction band edge, the valence band edge, the parabolic density of states approximation, the valence band and conduction band. So this is denoted by Gc of E, this is denoted by Gv of E. Gc of E is given by a constant A1 multiplied by root of E minus Ec, where A1, the quantity A1 is a constant which is given by 8 root 2 pi mn raised to 3 by 2 divided by HQ. Similarly, Gv of E is a constant A2 multiplied by root of, it is Ev minus E, where the quantity A2 is equal to 8 root 2 pi mp raised to 3 by 2 divided by HQ. So in this constants A1 and A2 we have two terms. One is Mn. Mn we call it as the effective mass of the electron. Effective mass of electron, and Mp is the effective mass of the hole. Normally Mn and Mp are not the same. Mn not equal to Mp. Remember, M0 is the rest mass of the electron. Okay, which is equal to the rest mass of the electron, which is equal to 9.1 multiplied by 10 to the power of minus 31 kg. The rest mass of the electron M0 is applicable only if the electron is in the free space. But in silicon crystal, the electrons are moving in a silicon lattice. These electrons will come under the influence of other particles. Okay, these electrons will come under the influence of holes, photons, phonons, silicon atoms, impurities, defects, etc. Due to that, what happens is the effective mass denoted by M star is equal to a quantity A0 multiplied by M0. A0 can be greater than 1 or A0 can be less than 1. That depends upon the situation. Literature gives what is the value of A0. This M star, we name it as Mn and Mp. So why M0 is replaced by M star? Because the electrons inside a silicon crystal are influenced by other particles. Due to that, we replace M0 with M star. So when you look at the Fermi Dirac probability density function, the Fermi Dirac probability density function f of E comma t is 1 divided by 1 plus e power E minus of EF divided by kt for all E and t. for all E and T. So when you plot the Fermi distribution function, so this is E in electron volt, this is your EC, this is EV. So you can see that the probability of finding the electron at higher energy state will be nearly 0. So the plot for the graph f of E comma t will be like this. So this is a plot of f of E comma t. So what is f of E comma t? That is a probability that you can find an electron at energy state E. There is a probability that the state E is occupied by an electron. But if you plot the probability of finding a vacancy, that graph will be going like this. So this is the graph. One minus of f of E comma t. This is a probability that an energy state is vacant. Energy state is vacant. So f of E comma t is a probability that you can find an electron at an energy level E, whereas 1 minus f of E comma t is a probability that an energy state is vacant. So we have seen that if E minus of EF is greater than 3 kT, we can approximate the Fermi distribution by using f of E comma t is approximately e power minus of E minus EF by kT. And if E minus of EF is less than minus 3 kT, then f of E comma t is approximated to 1 minus of e power E minus of EF by kT. So these two approximations we call it as a Maxwell Boltzmann approximation. We want to find out the intrinsic electron concentration in the conduction band. The intrinsic electron concentration in the conduction band is denoted by the notation NO. N represents the negatively charged particle. The subscript O represents equilibrium. For us, the equilibrium is 300 Kelvin. So we have the energy states E in electron volt. This is the conduction band edge, that is EC. The parabolic density of states approximation, this is GC of E. Okay. So if you look at the free electron concentration, in conduction band denoted by NO, how will you find out? We can take a small incremental energy level D This is the incremental energy level d. So what I do is I multiply Gc of E with d. This will give you the area of the strip, area of that strip, and then you integrate this equation from E equal to Ec to infinity. That gives you the total area under the curve, which is equal to 4n states. We know that the total number of states available 4n. But I know that as you go up the energy level, the probability that you can find an electron at a higher energy level is less. So what I do, I know the probability. The probability density function is this one. This is f of E comma t. So I multiply the above function with f of E comma t. Okay, so that what you get is, you get the total area under the curve. This area that is under this curve will give you the electron concentration NO. But what I do is I use approximation to find out this answer. So what are the approximation? 1. Parabolic density of states. Parabolic density of states approximation. Because we know that the distribution is non-uniform. Second, Maxwell Boltzmann approximation. Maxwell Boltzmann approximation. So what is the equation NO? NO will be integral Ec to infinity A1 multiplied by root of E minus of Ec into d divided by 1 upon E power E minus of Ef divided by kT. So using the approximation, what you get is, we get NO is integral Ec to infinity. It is A1 into root of E minus of Ec multiplied by d into E power minus of E minus of Ef divided by kT, using the Boltzmann approximation. Anyway, this equation is not integrable, so we just finally just jump to the final answer. By some method we have to integrate this equation. So that is not so important for us. So after substituting this value, what is this NO? NO is given by 2 times 2 pi mn k into t divided by h square raised to 3 by 2 e power minus of Ec minus of Ef divided by kT centimeter raised to minus 3. This is the answer we are going to get. So this is a concentration of carriers. In that, the first term is a constant, so we abbreviate this as Nc, e power minus of Ec minus of Ef divided by kT centimeter raised to minus 3. This is the electron concentration in the conduction band. So what is that Nc? The quantity Nc in the above equation, Nc is given by 2 times, it is 2 pi mn k into t divided by h square raised to 3 by 2. centimeter raised to minus 3. So this quantity Nc is called effective density of states in the conduction band. Effective density of states. In conduction band. This means what you're doing is we take the energy distribution in electron volt. We have a conduction band edge. We know that the distribution of energy states over the energy level is non-uniform and is approximated by the parabolic density of states approximation. And finally we get the concentration of carriers. You can see that the lower energy states are filled, and when you go higher up, the energy states are empty. So what we do is, the total number of states occupied by the electron is being lumped by using an impulse function at the conduction band edge like this. So there is an impulse function at the conduction band edge having a height equal to Nc. So this is an impulse function. Impulse function which is shown lumped at the conduction band edge. That is called the effective density of states, because I know that the lower states are filled, higher states are empty. So the total number of states occupied by the electron throughout the conduction band, we collect it and lump it at one point, that is at the conduction band edge having a height of Nc. Similarly, we can find the intrinsic hole concentration valence band. So you have the energy level EV, you have the valence band edge EV, the parabolic density of states function GV of E. So what I do first is I consider a small elementary strip of width D and find out the area under this curve. The area. So the concentration is denoted by PO. P for positive charge particle, O for equilibrium. So what is PO? PO can be written as the density of states function GV of E multiplied by D. That will be the area under the strip, and integrate this from minus infinity to the valence band edge EV. That gives the total area under this curve, which is equal to 4n states. But I know that when I go towards the lower energy states, the probability of finding the hole is negligible. So this is the probability of finding the hole, which is 1 minus of f of e comma t. So the area under this curve, this area, it is the hole concentration. So to get the hole concentration, it should be multiplied with 1 minus of f of e comma t. Okay, so this is equal to integral from minus infinity to EV A2 multiplied by root of EV minus E multiplied by D into 1 minus of 1 upon 1 plus e power e minus ef divided by kT. Okay, so the same approximation. So finally you end up with an answer 2 times, it is 2 pi times mp k multiplied by t divided by h square, the whole raised to 3 by 2 e power minus of, it is ef minus ev by kT, that means centimeter raised to minus 3. So this can be approximated to nv into e power minus of ev minus ef divided by kT, centimeter raised to minus 3. This is the concentration of holes in the valence band. So if you look at the effective density of states in the valence band, the effective density of states in the valence band is denoted by Nv, that is equal to 2 times 2 pi mp k into t divided by square, the whole raised to 3 by 2 centimeter raised to minus 3. This effective density of states in the valence band means when you look at the energy level in electron volt, this is the valence band at GV. We know that the distribution of holes inside in the valence band is non-uniform. So what you do is, we have a larger concentration of holes at the edge of the valence band, and when you move down, the concentration decreases. So we lump the total density of states occupied by the holes by using impulse function having a height equal to nv. So this is an impulse function. Like what you have done in conduction band. So we know that the valence band is filled, but certain bands are empty, but the distribution is non-uniform. So the total bands over which it is empty, we collect it and lump it at one particular point, that is at the valence band edge. Therefore we get an impulse function having a height equal to nv. So look at the carrier density in the conduction band and valence band. So this is what you discussed until now, but you know that we know that when covalent bonds break, EHPs are generated, electron hole pairs are generated. So you can see from here an electron that is moving from here to conduction band. So there is one electron in the conduction band, one vacancy in the valence band. So electron and hole pairs are generated. This implies that the concentration of electrons is equal to the concentration of holes, NO equal to PO, due to EHP generation. Due to EHP generation. So look at the carrier concentration in intrinsic silicon. We have NO equal to Nc e power minus of EC minus of EF divided by kT, centimeter raised to minus 3, and PO equal to NV e power minus of this EF minus EV divided by kT, centimeter raised to minus 3. Remember, the quantities NC and NV. This NC and NV is material dependent. Is material dependent, and also depends upon temperature. So if you look at literature, you get the values of NC and NV for all the different types of semiconductor. So what is law of mass action? In a semiconductor, when bonds break, EHPs are generated. EHP is generated. So this implies that the concentration NO equal to PO. Okay, this concentration NO equal to PO is defined as Ni. So what is that Ni? Ni is the intrinsic concentration, intrinsic electron concentration in semiconductor. Hence, we can write NO multiplied by PO is equal to Ni square. Okay, so this equation NO into PO equal to Ni square is called the mass action law. This is very important, mass action law. The value of Ni is actually a constant for a given temperature. Okay. So we want to look at what is the intrinsic concentration at T Kelvin. That is, we know that Ni square equal to NO multiplied by PO. So this will come out to be NC multiplied by NV e power minus of, you get answer EC minus of EV divided by kT after substituting the value of NO and PO. But I know that what is EC minus EV? That is equal to EG. So this will come out to be NC multiplied by NV e power minus of EG by kT. So what is Ni? The value of Ni will be equal to root of NC/NV e power minus of Eg by 2 kT, centimeter raised to minus 3. When you substitute the value of Nc and Nv, this answer will go to 2 times. It is 2 pi kT by h square raised to 3 by 2 multiplied by m and mb raised to 3 by 4 e power minus of Eg by 2 kT, centimeter raised to minus 3. That is the concentration Ni. But in simple form, we can write this one. This is equal to a constant B multiplied by T raised to 3 by 2 e power minus of Eg by 2 kT. centimeter raised to minus 3. Because B is a constant, and you can see that in the equation the variables are basically what? T and Eg. So you can see that the quantity Ni, you look at Ni depends on material, depends on temperature, and depends on band gap, depends on Eg of semiconductor material. So what is the significance of the intrinsic area concentration? So we know that Ni is equal to a constant B into T raised to 3 by 2 e power minus of Eg by 2 kT. Simple form, centimeter raised to minus 3. In the first point, take the natural log of Ni. We get answer natural log of B plus 3 by 2 natural log of T minus of Eg by 2 kT. You know that the natural log of B, this term is a constant. 3 by 2 log of T, that is negligible, we can neglect. So what we can do is we can plot a graph natural log of Ni versus 1 by T. Plot a graph. X-axis 1 by T, y-axis natural log of Ni. What you get is, in a small range of T, you get a graph like this. If you look at the slope of this graph, what is the slope? Is minus of Eg by 2k. So what is the significance is, you can see that the slope can be used to measure the band gap of semiconductor. So this is one of the method of measuring the band gap of a semiconductor. At the same time, we want to look at Ni for a temperature T upon Ni for 300 Kelvin. That will come out to be T divided by 300 raised to 3 by 2 e power minus of Eg by 2k bracket, it is 1 by T minus 1 by 300. So we can find out Ni for any temperature. Remember, at T equal to 300 Kelvin, if you just look at silicon, when you put in a table form, so we have semiconductor, the value of Ni in centimeter raised to minus 3 for the 3 types of semiconductor. So we have germanium, silicon, gallium arsenide. For germanium, it is 2.5 multiplied by 10 to the power of 13 centimeter raised to minus 3. For silicon it is 1.5 multiplied by 10 to the power of 10 centimeter raised to minus 3, and for gallium arsenide it is 1.8 multiplied by 10 to the power of 6 centimeter raised to minus 3. So you can see that the quantity Ni is a function of band gap as well as temperature. Okay, so these are the values for different types of semiconductor. We want to look at where is the Fermi energy level of an intrinsic semiconductor. So we know that NO equal to PO. This is normally due to ESP generation, electron hole pair generation. That means NC multiplied by e raised to minus of EC minus of EF by KT equals NV e power minus of, it is EF minus of EV by KT. So when you take it one side, so we can write this way: e power minus of 1 by KT. Take it out, it will be EC minus of EF minus EF plus EV equal to NV by NC, NV by NC. So from this we can get EC plus EV minus 2 EF will be equal to EC plus EV minus 2 EF is equal to KT natural log of so one minus n is also there. We get KT natural log of NV by NC. So what is EF? That EF we call it as a intrinsic Fermi level EFI will be EC plus EV by 2, EC plus EV by 2 plus KT by 2 natural log of NV by NC. This can be written as EC plus EV by 2 plus 3 by 4 KT, 3 KT by 4 natural log of MP by Mn after substituting the value of NC and NV. This goes approximately EC plus EV by 2. This is negligible. You can neglect. So the answer is EC plus EV by 2. So where is the Fermi level? The Fermi level is mid gap between the conduction band and the middle of the forbidden gap. We can also find out the Fermi energy level by using another method. The method is, since NO equal to PO, the probability of finding an electron in the conduction band, that is F of EC comma T, will be equal to the probability of finding a hole in the valence band. So F of E comma T is the probability of finding the electron, and 1 minus F of E comma T is the probability of finding the whole. Okay, so this will be 1 divided by 1 plus e power, it is EC minus EF by kT is equal to 1 minus of 1 upon 1 plus e power, it is EV minus of EF divided by kT, which is equal to 1 divided by, it becomes 1 plus e power minus of, it is EV minus of EF by kT. So this means that EC minus EF by kT is equal to minus of EV minus EF by kT. Therefore, we get EF is equal to EC plus EV by 2. We can call this as the intrinsic Fermi level EFI. So where is EFI? It is E mid gap, the middle of the forbidden gap. So what is the energy band model of the intrinsic semiconductor? So we have semiconductor having physical dimension x equal to 0, x equal to L. L is the length of the sample. So when you draw the energy band diagram, we draw with respect to free space. So this is E0. Below E0 we have the conduction band EC. The difference between the two energy levels is E psi, which is 4.05 electron volt. Remember that the semiconductor is silicon, so it is electron affinity for silicon is 4.05 electron volt, and then you have the valence band. The valence band and conduction band separated by the band gap, that is Eg. So where is the Fermi level? You can see the Fermi level will be mid gap, it will be here. We show by dotted line in the middle of the band gap. This is EFI. This is the Fermi level of intrinsic semiconductor. So what you have seen in this topic, one, we have seen the density of states approximation, the density of states approximation. The approximation is used because the distribution of energy states is non-uniform. So we use a parabolic density of states. Then after that, we look at the free carrier concentration in conduction band and valence band. That is, we got expression for the concentration of electron, the concentration of hole, NOPO. Then we have seen the significance of Ni. So if I know the concentration Ni, it is possible for you to find out the band gap of semiconductor. Then we have introduced the mass action law. Mass action law is very important, which says that NO multiplied by PO equals Ni square. And then we find out what is the intrinsic Fermi level. Intrinsic Fermi energy level. denoted by EFI, and where is the location is. So that is about this topic. Thank you.